Hi, today we will see how to explicitly understand the derived category we defined in the previous lecture as a localization of this category K of A by giving quite explicit descriptions of the mapping spaces. In particular, we will describe them as a special kind of colimit of mapping spaces in K of A and see that in many cases they even directly agree with mapping spaces in K of A. In particular, we will see that limits and colimits in D of A are quite easy to compute. They're usually just given by lifting the diagram to a diagram in K of A and computing the colimit there. Hi, I'm Achim Krause from Mathematics Münster. So recall that we defined the derived infinity category of an abelian category as a certain localization, namely as the Dwyer-Kahn localization on at all quasi-isomorphisms in the category K of A that we defined last time, which was this quite explicit infinity category with objects given by chain complexes, morphisms given by actual maps, and then somehow chain homotopies between them and higher stuff like that. So our goal today is to describe the mapping spaces in this derived category more explicitly. And now, in general, describing mapping spaces in Dwyer-Kahn localizations is very subtle and difficult. And in fact, a lot of abstract homotopy theory has been developed explicitly to tackle this problem. So, for example, Quillen's model categories, and another thing to name is Gabriel Zisman's calculus of fractions. Those are tools that allow you to describe under certain assumptions on the category you input and some extra structure on the category you input, how mapping spaces in this localization look like. So we will see today that somehow in this case, in what's happening here, the description is much, much simpler and we won't need all that language. And, but to do that, we will need some additional terminology. So we will talk about slice categories and filtered colimits today as sort of a byproduct of this goal. So let's get right into that. If C is an infinity category and X in C is an object, then we define two other infinity categories. One is the slice category over X, which is obtained by taking just the diagram category of functors from delta 1 to C. And then we can look at the map D0, which sends every arrow to the object at its target. And we pull that back along the map from delta 0 into C. That sends the point to X. And dually, we can, of course, also form the slice category under X, which is the corresponding pullback, but where now we've taken the D1 that sends every arrow to its source object. And you should think about this as having objects, diagrams of the form some object of C with a map to X, and this one as having objects, diagrams of this form. So this should explain why this is called the slice over X, or the over category of X, and this similarly the slice under X, or under category. In terms of that, we can now define something like a category for fixed objects of K of A, a category of quasi-isomorphisms over that object. So what does that mean? So for C in K of A, we write Ka slice over C, and then upper Qi for quasi-isomorphism for the full subcategory of the slice category over C. On all objects C prime to C where the map is a quasi-isomorphism. And dually, we can define something like a quasi-isomorphism category under C as a full subcategory of the slice under C. And what we will discuss today is the following description of mapping spaces in D of A. So maps in D of A from C to D for any complexes C and D. Again, we're thinking, since we know that the Fourier-Kahn localization is always fully faithful, we can think of objects, or we can describe this category by just thinking of it as having the same objects as K of A, but different mapping spaces. So these are just complexes. So maps between any two complexes will be a colimit over this category Ka Qi over C, and then I have to say up here, and then we're taking map in Ka out of blank into C. So objects in here are some C prime sitting over C, and the factor we're considering sends that to C prime comma D. And dually, we also can describe this as a colimit over the slice of quasi-isomorphisms under D on map Ka C comma blank. And again, this means that somehow we're looking at a functor which takes D prime under D to the mapping space from C to D prime. And so we won't prove that today. I mean, to prove that rigorously, we will need, there's some technology involved that we won't fully develop in this course. But instead, we want to apply it and somehow develop some intuition for it. So here I want to note something. So in principle, this is a little bit sloppy. The problem is that map, as we defined it, right? We defined for any two objects of an infinity category a mapping space. So as we defined it, it's not is not a functor from, say, C op cross C to spaces. And the problem is that composition is not strict enough, right? So we saw that even just pre-composing with a single morphism, we have to make some choices. So, in other words, as I wrote this here, this doesn't really define a functor. And now there's several ways around this. So you could note that somehow both this Ka and the infinity category of spaces came to us as homotopy coherent nerve of simplicity enriched categories. And on the level of simplicity enriched categories, you can really write down functors such as hom blank comma d. So you could take this functor here in this specific situation to just denote whatever you get by applying the homotopy coherent nerve to the functor hom blank comma d on the simplicity enriched categories. So that would make the statement fully rigorous. In general, there is some somewhat involved machinery of turning the mapping space into an actual functor. And that's called straightening. It's somehow a large part of the technical difficulties in working with infinity categories. But we will simply be a little sloppy when it comes to writing down these things. If you're interested in the technical details, check out any of the very good resources that we linked in our first video of our course on infinity categories. So we have this result, and let's at least see how to get a map from here to here. So turns out, since quasi-isomorphisms in K of A actually become equivalences in D of A, right, by construction, it's a localization. We have that this colimit over there of Ka Qi over C op map Ka blank D. Straight D, sorry. This maps, of course, I mean, modulo these problems with that the map as we wrote it down is not a functor. This maps to the same diagram where we now put map in dA. Right? That's just, think of this as just applying the functor. The functor gives me a map between mapping spaces, and if you believe that you can turn map into a functor, then it should be compatible with the diagram. And so this, on the other hand, this is now really a diagram where all the maps are equivalences, right? Every quasi-isomorphism induces, right? Every map in here is in particular a map between C prime and C prime prime. And since quasi-isomorphisms have some 2 out of 3 property, if I have a map like this, then if these two are quasi-isomorphisms, this is one too. So every map in here induces a homotopy equivalence on mapping spaces, right? We've constructed dA in such a way that the quasi-isomorphisms are already equivalences in here. And so this is somehow a constant diagram. It's a diagram where all the maps are equivalences and somehow in a canonical way. And so this you should really think of as just being map from C to D. To see what this colimit formula gives us and to describe mapping spaces in D of A in specific cases, let's make the following definition. We call a complex C in K of A K projective, and that K is just the fixed letter K. It comes from the name of the category. If map in K of A C comma blank sends quasi-isomorphisms to homotopy equivalences. Right, this takes a map between complexes to a map between the mapping spaces, and we can ask whether that's a homotopy equivalence. And similarly, we call it K injective if map blank comma C sends quasi-isomorphisms to homotopy equivalences. And as a corollary to the colimit formulas that we saw previously, we see that if C is K projective or D is K injective, we actually have that map dA from C to D is equivalent to map Ka C to D. And that's simply because, so a priori, this is a colimit over this slice diagram. Every object in the diagram comes with a map from this one. But if mapping into D preserves quasi-isomorphisms, if D is K injective, then these maps from this one into map C prime comma D are all equivalences. And so these equivalences give us an identification between the given diagram and the constant diagram at this one. And so the colimit is simply this. And dually, we can use the other colimit formula to see that if C is K projective, the other colimit is constant and gives us simply this. And as a little remark, to get a feeling for this condition, K projective or K injective, recall that there's this so-called fundamental lemma of homological algebra, And it's depending on how it's stated, it sometimes says something about maps from a projective resolution to a chain complex or something like that. But one version of it is actually equivalent to the fact that bounded below and level-wise projective for a chain complex implies that it's K-projective. And similarly, bounded above, the dual version, and level-wise injective implies K-injective. So there's this slight subtlety that if you're doing homological algebra with unbounded complexes, sometimes being level-wise projective is not enough in places where being level-wise projective is enough if you work with bounded below complexes. This is the reason. Somehow K-projective is the right notion in full generality. And in our current setup, we see that very nicely. This is exactly what we need in order to get sort of an explicit description for these mapping spaces. So, in particular, now in this language, given C in K of A and a quasi-isomorphism from C prime to C with C prime K-projective. So think of this as some kind of projective resolution. Then map from dA C D, map from C to D in dA can be computed by, well, first replacing the C by a C prime. In D of A, quasi-isomorphisms are equivalences. And then applying our previous observation, right? So this can be computed as just maps from C prime to D. And now this is a space whose pi 0 is just chain homotopy classes and so on. So this is explicitly telling us about the mapping space here. And you'll see that this is basically the usual formula that people give for the derived Hom, where you say that, oh, you just pick a projective resolution for the domain. And of course, dually, if you have a quasi-isomorphic replacement for D, which is K-injective, you can give a dual formula by going maps from C to D prime. And the nice thing here is that we haven't built anything like a choice of a resolution into the definition, right? We've defined this D of A by a universal property, but we still get this kind of thing, this kind of usual formula out of the formalism if we need it. And the other nice thing to note here is that we haven't required in our construction that you actually have projective or injective objects, right? This is just the statement that if you have them, you can use them to compute your mapping space in a nice way, but the category makes sense independently of that. So what we want to do now for the rest of the lecture is we want to understand limits and colimits in dA. And note that by this observation, if every complex is actually quasi-isomorphic to a K-projective one, then every limit cone in K of A goes actually to a limit cone in D of A. Right? We test whether we have a limit cone by mapping into it. If every object can be represented by k-projective one, then it suffices to check against those, but then somehow the mapping spaces are the same, so being a limit cone in either of the categories is the same condition. And similarly, if every object can be represented by a k-injective one, then colimits from k of A to D of A are preserved. So we'll see now that actually we don't need to require that if we just care about finite limits and colimits. So we saw in the previous lecture that k of A has all finite limits and colimits, and we will see that the same is true for D of A, and that the functor preserves all of them. So to talk about limits and finite limits and colimits in general in D, in D of A, we will need some stuff about filtered colimits. So an infinity category C is called filtered if for any finite simplicial set K, and here finite means, of course, not that it's finite in total. It also doesn't mean that it's level-wise finite. It means that in total there are finitely many non-degenerate simplices. Same as as we used it when we talked about finite limits and finite colimits. So for every finite simplicial set and every map K to C, so we call it filtered if every map out of a finite simplicial set extends over the simplicial set K cross delta 1 pushed out along K cross 1 with delta 0. Right, and how should you think about this? Well, this basically just takes your simplicial set and forms a cone directed to the right. And dually, right, there's always a dual notion. Dually we call C co-filtered if C op is filtered. If you unwrap what that means, then you see that it means the same thing with this cone replaced by the one that faces the other direction. Right. So at this point, it's a very nice exercise to see that this notion of being filtered actually agrees with the one categorical one if you have the nerve of a one category. So explicitly, there's this notion of what it means to be filtered for one category. It means that any two objects map to a common one, and that any two parallel morphisms can be co-equalized with another map. Like that somehow, if you have two parallel morphisms from A to B, you find a map from B to C such that they become equal. And so the claim is that the nerve of C is filtered in this infinity categorical sense if and only if C, for one category C, is filtered in the usual sense. So when we speak of filtered colimits, this just means these are colimits indexed over filtered diagrams. Similar to how finite colimits are colimits indexed over diagrams which are finite as simplicial sets. And dually, we speak of co-filtered limits. And one immediate example that could come to mind here is if your category actually has colimits, right? Here we're asked to find some cone, but if your category actually has colimits, then you're finding more than that, right? You're finding some universal cone. So it's actually immediately true that if C has colimits, has finite colimits, then it's already filtered. So this is a weaker condition than asking for colimits. And so the crucial property of filtered colimits is the following fact. So if I is a filtered infinity category and J is a finite simplicial set, and we have the following diagram. If we start with a functor from I cross J to S, where S is the infinity category of spaces, then we can first take the colim in the I direction. Right, this does use more than we technically know about colimits, right? This does use that somehow colimits are functorial or can be chosen in a functorial way. We've seen earlier in one of Thomas's lectures that the universal property of colimits actually characterizes them up to some kind of contractible choice. So they're really unique in a very strong sense, but you're still making that choice when you want to actually write down a functor and pick colimits. So there's something that we're sweeping under the rug here. Similar to functoriality of mapping spaces, there's some machinery involved in actually picking functorial colimits, and we'll take that for granted. So we can take the colimit in the I direction, but we can take also the limit in the J direction. And we can fill this diagram to a square by then doing the other thing. Right? So we're taking somehow a filtered colimit and a finite limit at the same time. And now generally, there are somehow statements like colimits of any shape commute with colimits of any shape, and limits of any shape commute with limits of any shape. But colimits and limits typically do not commute. It's not hard to write down all kinds of counterexamples in all kinds of one categories even, so this should not surprise you. But what might surprise you, if you've never thought about filtered colimits, is that this diagram does actually commute. In other words, if we take a filtered colimit and a finite limit, the order doesn't matter. Filtered colimits commute with finite limits in the infinity category of spaces. So that's somehow a property that the infinity category of spaces enjoys that's not true in very general infinity categories. And one can prove that by reducing to the case of J being a pullback diagram, right? We know that somehow if you if a functor preserves finite limits, if and only if it preserves terminal objects and pullbacks. Thomas proved these decomposition tricks for us. But in the case of a pullback, there's some actual work involved. It should surprise you because this only holds for the infinity category of spaces. It's not a completely abstract statement. Maybe so we won't prove that here, but as an exercise, it's instructive to check a special case of the analogous statement in the one category of sets. So the claim is that filtered colimits in sets commute with finite products. So I recommend you to see what's going on there, and if you want, you can even do pullbacks, but it's a little more combinatorial exercise. Well, so that's one very central property of filtered colimits. The other, that actually follows from this, is that if K in spaces comes from a finite simplicial set in the previous sense, so it has finitely many non-degenerate simplices, so this is somehow like a finite complex, then the functor map out of K from spaces to spaces commutes with filtered colimits. And again, that's not something you should usually expect, right? We had some characterization of colimits by maps into something. So for colimits, in general, maps into something turned colimits into limits. And similarly, mapping out of something always commutes with limits of any shape, but usually not with colimits. So something funny is going on here. But note that the analogous statement in the one category world for sets actually follows directly from the exercise I just gave. So if you have a finite set and you map into something, that just takes a product, right? So if you think about sets instead of spaces and K is a finite set, then this map would just be, like this functor would just take a Cartesian product, a finite Cartesian product of your object with itself. And we said earlier that filtered colimits in sets commute with finite products. So think of this as some extension of that. So there's a very useful corollary to this filtered colimit description, or to this fact that mapping spaces out of finite spaces like K, spaces coming from finite simplicial sets, commute with filtered colimits, and that's that also if you take the functor that takes homotopy classes of maps out of K. So the usual notation in homotopy theory is something like square brackets K comma blank for that. So this means just pi 0 map K blank, right? This is a functor from S to the one category of sets, so to the nerve of the category of sets. This functor commutes also with filtered colimits. And the proof simply consists of the observation that pi 0 as a functor from spaces to the one category of sets, or its nerve, commutes with all colimits. Proving that something commutes with filtered colimits is tricky because we don't have some machinery like these decomposition tricks that Thomas proved in the lecture on colimits. But proving that something commutes with all colimits is something we know we can check just on coproducts and pushouts. And so this is maybe a good exercise in recalling how colimits in the infinity category of spaces were defined to check that this really commutes with coproducts and pushouts. We will actually see later that this functor commutes with all colimits for a more direct reason, namely it's left adjoint to another functor, but let's not go into that now. So now, how does this come in our discussion of the derived category? Well, as you might have guessed, the claim is that the colimits that we discussed in this formula for mapping spaces of the derived category, those are actually filtered colimits. So these categories of quasi-isos under a given object C and quasi-isos over a given object C and then up, these were the indexing categories of the colimit diagrams there, are both filtered. And to prove that, we simply check that this one has colimits and that this one without the op has limits. Right, that's enough. As we observed earlier, anything with colimits is already filtered, and anything with limits is already co-filtered. So the way we check that is that this guy, remember this was defined as a full subcategory of this slice category. This is closed under colimits in there, right? So given a diagram in here, we can form a colimit in that category. And then the claim is that the tip of that cone still lies in this full subcategory. And so the cone, the colimit cone in here, gives me a cone in here, which is a colimit cone, right? Strictly speaking, we don't need that it still is a colimit cone. We just need cones to know that we're filtered. But yes, so this implies that this has colimits, and they're computed by computing them in here. And I guess we haven't seen that colimits, how colimits in these slice categories work. So they exist in general, and somehow one can work out that pushouts in the slice category are just computed as pushouts in the underlying category, and the initial object is C with the identity. So you have pushouts and an initial object that gives you finite colimits. You can even get arbitrary colimits. Arbitrary coproducts are something like pushouts over C. Well, let me not go into that. Let me rather say what I'm using about colimits in here. So we have a functor from this entire slice category down to k of a itself, and we call that cofiber. And why is that? Well, it's supposed to take the object C to C prime to the cofiber, i.e. The push out of a diagram like this, where you've put a morphism to the zero object here. So, strictly speaking, I've only explained what it does on objects, but you can write it as a composition if you put some diagram category in the middle of diagrams like this, and you believe that somehow there's a functorial choice of colimit, and that somehow, and then you have to check something like that. Forgetting from such a diagram down to such a diagram is an equivalence, because somehow there's a contractible choice of morphisms to the zero object. Let me be a little sloppy with that and just claim that we have this cofiber functor. So that functor preserves colimits essentially because it is somehow itself a colimit. And we can characterize this full subcategory of quasi-isos in terms of this functor. Namely, we have that C to C prime is a quasi-iso if and only if the cofiber of C to C prime is acyclic, has trivial homology, is quasi-isomorphic to zero. And it's, for example, you can check that in terms of the long exact sequence. So they're with the formula for pushouts that we gave in the previous lecture on the construction of the derived category, you can see that the cofibers sit, the homology groups of the cofibers sit in a long exact sequence with the homology groups of C and C prime, and so this directly follows from that. So if you know that this functor preserves colimits and it somehow detects quasi-isomorphisms in this way, then our claim that the quasi-isomorphism objects are closed under colimits in here amounts to checking that acyclic objects in K of A are closed under colimits. And for that, you again just have to check that they're closed under pushouts and arbitrary coproducts, and both of that should be clear just from the definition of pushouts and coproducts in K of A that we gave in the previous lecture. But of course, one can also directly just check this from an explicit description of how colimits in the slice category work. If you know that colimits are taken underlying, that pushouts are computed underlying, then it basically follows from the same ingredients. And of course, this only handles this one, but then there's a dual argument using limits in this slice category. So we're now finally ready to prove that the derived category has all finite colimits and limits, and we can compute them in K of A. So the statement is that the derived infinity category D of A has finite colimits and limits, so finite colimits and finite limits, just to be clear, and the functor from K of A to D of A preserves them. So to prove that, we need to see that we have an initial and a terminal object. We need to see that we have pushouts and pullbacks, and we need to show that the functor here preserves all of those. So to get terminal and initial objects out of the way, this just amounts to saying that 0 is still terminal and initial in D of A. Right, and what does that mean? Well, I mean, for example, you can just compute, or I guess we can even appeal to our previous result. 0 is K projective and K injective. So maps out of 0 and into 0 can just be computed in K of A. So it's still terminal and initial in here. So that's fine. So now we need to deal with pushouts, and as usual, and pushouts and pullbacks, and as usual we'll discuss pushouts, and then we'll see that somehow pullbacks are a dual argument. So let's first check that the functor actually preserves pushouts. So given a pushout diagram in K of A, we need to check that this is still a pushout in D of A. And let's write down what the universal property of that pushout amounts to. Well, it amounts to saying that if we take maps in K of A from this into any E, so from D into E, from B into E, from C into E, and from A into E, then this is a pullback in spaces. And then the corresponding diagram, where we take map in D of A, we not fill the other corners, just the same thing with D of A instead of K of A, then this diagram arises by the colimit formula as a filtered colimit of diagrams like this one, let's maybe call this star, of versions of star for objects E prime from this slice category. Right, so there's this slice category, K of A, Qi, slice under E, and the colimit formula for maps in D of A states that these mapping spaces can all be described as taking over this category a colimit of map D comma blank, map B, comma blank, and so on. But each of these diagrams, right, and in the colimit formula, we're taking maps in K of A, right? So each of those diagrams is a pullback, and since filtered colimits commute with pullbacks, this is a colimit. This is a pullback, sorry. So this is why we preserve pullbacks, and it follows from that we, why we preserve push-outs, it follows from that we preserve finite colimits in general. What about the other thing we need to show, right? This just shows that if we have a colimit up here, it gives us a colimit in D of A, but we're claiming, in principle, a little bit more. We're claiming that colimits in here exist in general. So there could be a diagram down here which just doesn't really have a counterpart up here. So it doesn't make sense to compute its colimit upstairs. So let's check that that doesn't happen. So what are we doing? Well, so for the existence, we start with a diagram of A, B, and C. But now this is a diagram in D of A. And we want to show that it admits a colimit. If this diagram would already come from K of A, so from actual maps between these complexes, then we would be done, right? Then we could just compute the colimit upstairs, and that gives us a colimit downstairs by what we just proved. But a priori, we can't do that, right? Mapping spaces are different down here, so there might just not be a morphism from A to C up in K of A that lifts this one. So this is where our understanding of really homotopy classes in terms of filtered colimits comes in. So let's see what the colimit formula actually tells us about equivalence classes of maps. And as we remarked earlier, pi 0 commutes with colimits. So somehow this description of mapping spaces gives you the same kind of colimit formula on pi 0 of mapping spaces, on equivalence classes of maps. Right? And remember, this is just a set, right? So this is now a filtered colimit of sets, no fancy spaces or anything. And in spaces, filtered colimits are actually, well, in sets, colimits are generally just computed by, well, elements of the colimit are represented by elements in any stage in your colimit, and there's some equivalence relation on those. So this means that my abstract map in here actually comes from something in here in like a certain stage. So if you unwrap what this means, then it tells you that there exists for our given map A to C a quasi-iso C to C prime, in other words, an object of the indexing diagram here, such that the composite from A to C prime actually comes from K of A. Right. This is what this colimit formula tells you about map from A to C in terms of all the maps from A to C prime in K of A. And Now, if we do the same trick for the map from A to B and put all in the same diagram, then this tells us that our original diagram here actually maps to another diagram. We've taken the identity on A and this quasi-iso from C to C prime and this quasi-iso from B to B prime. And the claim is that this diagram down here, or by construction, this diagram down here, this row comes from K of A. Right? This is a diagram in D of A, but we're saying this row of it that actually lifts to a diagram in K of A. So this has a push out. And now the upper row is an equivalent diagram, right? This is really a natural transformation, which is pointwise a natural equivalent, which is pointwise an equivalence, right? It's a natural equivalence between these functors. So, because quasi-isos are equivalences in D of A, so it follows that the colimit of this row also gives you a colimit of this row. So, since this row comes from K of A, its colimit exists in D of A, and the upper row is equivalent as diagram. All right, so this finishes everything we needed to say about colimits, right? If pushouts exist, finite colimits exist, so since we have a zero object, so we're done. And pullbacks is the same trick, you're just using the other colimit formula instead. So that basically finishes what we wanted to do for today. There's one more kind of word of warning I wanted to give. So we've constructed D of A as this localization of a very explicit infinity category, K of A. And we've seen that we can get very good control about the mapping spaces. In cases where we do have these K projective and K injective objects, we can actually just use the same mapping spaces. But even in general, we have this formula expressing the mapping space as a filtered colimit, and because of the properties of filtered colimits, we get all this nice behavior that somehow limits and colimits in D of A are basically always computed by lifting the diagrams up to K of A and computing limits and colimits upstairs. So in some sense, this is a very tame Dwyer-Kahn localization. And just for fun, just to give you a feeling that this is not the norm, somehow we've used something very special here. This Dwyer-Kahn localization is actually what's also called a Verdier quotient of infinity categories. So something special going on. Let me give you two other statements to kind of contextualize that without proving them. So firstly, if we just take the one category of simplicial sets, we forget the enrichment and anything, and we just take its usual nerve as a one category. So there's no homotopy coherent nerve here, anything. But then we invert, we localize at a certain class of morphisms, namely the weak equivalences between simplicial sets. then you actually get an infinity category that's equivalent to the infinity category of spaces. So here W is weak equivalences. And so you see here that somehow over here the mapping spaces before localizing were really discrete. They were just the sets of maps between simplicial sets. No extra information. But as soon as we perform this localization, suddenly we get all these intricate mapping spaces that remember all the higher homotopy groups and all that. And also colimits, even though this has colimits and this has colimits, they're typically not preserved and you can't always compute them on simplicial sets, right? And in fact, it's precisely this kind of insight, even though he didn't state it in precisely this formulation. I think this notion of localization is due to Dwyer and Kahn, basically. But even before that, Quillen set up his machinery of model categories exactly to tackle these kinds of questions, right? That allows you to answer which colimits over here can be, which colimits over here can be computed over here, if you say it correctly. And so we see that this is kind of a very prototypical example of a wild localization where weird things happen. And kind of similarly, and closer to what we did in this and the previous lecture, we can also do something similar to chain complexes. So if you just start with the one category of chain complexes, take its usual nerve, and then invert all quasi-isomorphisms, then it turns out you actually get this derived category that we've been talking about, the derived infinity category. So one could have taken this as a definition as well, but then we wouldn't know how to say anything about this. So the good thing about this definition we used, which is essentially Verdier's construction, is that it allows you very good control over the mapping spaces and over limits and colimits from something that's quite explicit, right? K of A is still something where we just basically we built in mapping spaces in terms of the chain complex enrichment. And maybe to get some feeling for why this could be true, there's another thing you can do. So this is with W quasi-isomorphisms. And there's another thing you can do, which is you can invert just chain homotopy equivalences. And since every chain homotopy equivalence is a quasi-isomorphism, but not the other way around, what you're getting here will map to this. And it turns out here you're getting exactly this infinity category K of A. So in other words, the definition we gave for D of A can be contextualized, if you believe these two statements, in the sense that somehow this is an intermediate localization. If you want to understand this localization at once, you can first localize at the subset of quasi-isomorphisms, which is actually given by chain homotopy equivalences. You arrive at this, but then you still have to localize at the remaining quasi-isomorphisms. And localization is composed. That's just true from the universal property. All right, that does it for today. Thanks for watching, and I hope to see you in the next video.